Scientists and engineers at the University of Washington have demonstrated the first near-zero power devices capable of transmitting data across a distance of kilometers. They hope to begin selling the low-cost devices within 6 months. In the coming years, miniaturized, flexible electronics and other sensors could be integrated into our clothing, homes, vehicles and bodies as the Internet of Things IoT continues to grow. However, these subtle devices are not able to accommodate bulky battery packs. On the other hand, low-power devices struggle to communicate with other devices, particularly at a distance of greater than approximately 1 meter. This long-held barrier severely limits their use in IoT applications. The vision of embedding connectivity into billions of everyday objects runs into the reality of existing communication technologies, the University of Washington team writes. There is no existing wireless technology that can provide reliable and long-range communication at tens of microwatts of power as well as cost less than a dime. Now, these researchers have produced a solution in the shape of a long-range backscatter system capable of transmitting data across distances of up to 2.8 kilometers at extremely low power and cost. Until now, devices that can communicate over long distances have consumed a lot of power. The trade-off in a low-powered device that consumes microwatts of power is that its communication range is short, said Professor Shyam Golakot of the University of Washington's School of Computer Science Engineering. Now we've shown that we can offer both, which will be pretty game-changing for a lot of different industries and applications. The backscatter system transmits data using reflected radio signals. It consists of a source to emit a signal, sensors to encode information in reflections of this signal, and a receiver to decode information. While other backscatter systems struggle to decode signals, this system is equipped with a new type of modulation which spreads the signal across multiple frequencies, allowing for greater sensitivity. The communication system consumes 1,000 times less power than existing technologies which transmit data over comparable distances. The device can harvest electricity from ambient sources or run on a very cheap printed battery. The researchers tested their device in real-world settings, and were able to achieve reliable signal across a 41-room office, a 446-square-meter house, and a vegetable farm covering 4,046 square meters. This potentially enables a huge range of interconnected devices, particularly biomedical devices for data collection, in the emerging Internet of Things IoT, such as patches for joints which capture the range of motion for patients with arthritis, or sensors which use sweat to detect fatigue in soldiers. The researchers also hope that they could be used as sensors by farmers to track soil temperature and moisture, or to monitor pollution, noise and traffic in cities. People have been talking about embedding connectivity into everyday objects such as laundry detergent, paper towels and coffee cups for years, but the problem is the cost and power consumption to achieve this, said Dr. Vamsi Talla, who worked on the project at the University of Washington. This is the first wireless system that can inject connectivity into any device with very minimal cost. The system will be commercialized by Jiva Wireless, a spin-out founded by the team of engineers behind the device. The company has already built a contact lens and skin patch prototype, and hope to begin selling their sensors, which could cost as little as 10 to 20 cents each, within 6 months. The IoT's emergence with the introduction of virtual home assistants and other smart domestic devices has encouraged many teams to develop low-power devices which could be integrated into the IoT, including self-shading windows and a chip for automatic speech recognition.